Let us continue our journey into the fishing dynamics and the fishing industry. A reminder, last time we were here, we wanted to establish what was the steady state stock of fish. How do we do that? Well, the growth of the fish stock of fish is essentially the natural growth, so how many fishes are born, minus how many are harvested at every period t. So what do we know about this in the steady state? Well, we know that the stock must not change. That's what steady state means. So delta S star has to be equal to 0. So we simply use this fact to simplify this expression, and we find that the steady state stock of fish, S star, is actually a function of the steady state number of boats, B star. It's a negative function because more boats in the ocean, fewer fish are going to live. But are we done? Well, no, because both are variables. So what we want is an equilibrium that's just a function of the parameters of our problem. So here we only have one equation. We need a second one. And to do that, we're going to have to make some assumptions about how the fishing industry works. So let's start with the simplest one. So free entry fishing. So just think for a second, what do you think that means? How is it going to reveal itself in the equations? Well, if you remember your microeconomics, free entry means that every firm is able to enter, and it is sort of code for they're going to enter as long as they have some profit that they can make. And in the long run, then all firms that can enter will, and this is going to drive the profit margins to 0. So let's just go ahead and do that. So private fishermen enter the market as long as there are positive profit to be made. So what does that mean? Well, let's remember what our profit function is. So it's pi of S. So now let's write S star, because it's a function of so what we're looking at is the profit in steady state. So it's a function of the stock of fish in steady state, and it's equal to price of fish, P, times catches in steady state. So alpha S star of B star. And there, here I'm going to write F, because that's the number of boats in the free entry fishing case, because we can have other cases. So just to indicate that this is the number of boats that we have in the free entry case. And of course I have the cost of my boat to pay and all the other things, so minus C. And the condition is that this has to be equal to 0. So what I can just use is that this left part here has to be equal to that left part here. So the revenue per boat is price of fish times catches that are a function of the stock, which is itself a function of the number of boats, and has to be equal to the cost per boat. So we just simplify everything and we can find what's happening. So let's go ahead and do that. So now what I can do is substitute S star of P star F. So this was equal to K times 1 minus alpha. And now this is going to be B star F divided by R. So this was our expression for the steady state stock of fish. This has to be equal to C, so let's go ahead and do bunch of simplification. So what we can do here is multiply this in the parentheses. And then what we can do is, well, let's just, what we want, of course, is the steady state number of bolts. So let's multiply by -1 and and subtract this on each side. So we get this minus C. And now let's just divide and multiply by everything to get BF here. So just to see what's going to happen. Here I have R divided by this thing here, and let's just multiply a bit inside the parenthesis. So let's divide by P alpha K here, so we get just 1, and here we get divided by P alpha K. And here what's left is R over alpha. Yeah, let's have a big parenthesis for that. So this is our expression. Oops, and then there's no R here. Before interpreting our solution, I just want to show you graphically what we have just done. So as a reminder, what we did is we set the revenue per bolt equal to the cost per bolt, and you can see that the revenue per bolt is a function of the number of bolts in the ocean. So graphically what this looks like this. So the revenue per bolt function is P alpha K minus P alpha squared K over R times B star, the steady state number of bolts, and the cost per bolt is C. So this means basically if I'm the only fisherman in the world, I enter the sea to fish, then what's my revenue per bolt? Well, it's P alpha times big K, because there's the total carrying capacity, the total number of fish in the ocean that's available for me. But the thing is, I'm not the only one who does that, and eventually my competitors enter the market too, so B star enter, and you can see that my revenue is going to decrease as a linear function of B star. So people enter, and then we reach this steady state quantity of bolts in the ocean. We label it B star capital F for free entry, where the marginal revenue for one extra bolt is this expression there, has to be equal to the marginal cost of one extra bolt. Now let's go back and just interpret a bit our expression. So we had B star of F is R over alpha times 1 minus C over P alpha K. So things that make intuitive sense right away is, for instance, if it costs more per boat, then the number of boats in the industry is lower. If there's better price than for a fish, then people are going to want to fish more. So in a sense, this is the real cost of renting a boat. That's a negative function of B, or the reverse rather. If there are more fishes in the ocean, then that's good, because there's a minus, but it's at the denominator. So that's the more fishes in the ocean, I know that there should be a larger number of boats in equilibrium. One thing that I want you to consider is, what about fishing efficiency? Fishing efficiency is alpha. So just to tell you, so it was here. So the harvesting is alpha multiplied by B star S star. So that's the percentage of the whole sea that one boat catches. So is that is B star F a positive or a negative function of alpha? Well, if you just look at the expression, you see that it's not that clear. Because there's alpha the denominator here and alpha the denominator here. One alpha means that I have a better profit per boat for fishing because I am more efficient. So that's this alpha here. So more if I have better technology for my boat, it's better for me. But then there's this funny extra alpha that appears here. What does that do? Well, that's the feedback from the fact that all my competitors are also having better fish finders and GPS and trawlers to catch all the other fishes. So this means that it's going to depress the equilibrium stock of fish to catch. So I'm better at catching the higher percentage of the whole stock of fish if I have better technology, but the whole stock of fish is lower. So that's all all that is ambiguous about the impact of technology here compared to say the Soros-Swan model in which technology always improves standards of living and make people more productive. Here, since it's also going to depress the equilibrium stock of natural resources, then there's this ambiguity, and it doesn't seem like technology is all that good.